How often do you find yourself checking the weather before stepping out? For many, it guides our morning decisions, from dressing appropriately to choosing a hot coffee over iced. We've mastered predicting weather changes, unleashing the power behind prediction of the future. In a similar sense, our team at John Deere is trying to predict the demand that consumers and dealers alike will have for a product such that John Deere can have the inventory ready to deliver. This helps John Deere prevent massive under and overstocking of products, both of which can be detrimental to any business.
Just like meteorologists predict future weather based on past patterns, our development team employed time series forecasting to anticipate the future demands of John Deere's goods. We were guided by questions like how can we ensure optimal inventory levels to meet consumer demand? How can we help reduce the delivery downtime based on dealer requests for parts? With over 1.6 million unique part location combinations, our goal was to develop a 12-month forecasting for the demands of each part at each dealer location.
We began exploring a singular part location combination, attempting to identify its trends, seasonality, and other underlying components. This singular part location data produced 12-month seasonality, indicating a cycle of 12 months, meaning we can expect a similar demand quantity every calendar year. Trends help us justify why there are peaks and valleys in our data. For example, some part locations contain peaks in February and August, indicating preparation for tillage and harvesting season. In addition to trend analysis, we developed benchmark models such as seasonal naive, moving average, simple linear regression, and others to understand their strengths and limitations. After determining that these simpler models couldn't fully handle the seasonality trends, we implemented two advanced models in exponential smoothing and seasonal ARIMA to account for this.
With the behavior of one part location understood, we scaled our efforts, classifying each combination into categories including lumpy, smooth, erratic, and intermittent. And these were based on demand patterns and showcased in the tree map chart. The visual depicts a smooth par location located where the forecast was overpredicted. We applied targeted models for each category, constantly iterating and refining our approach by subclustering and reassessing. To quantify the effectiveness of our models, we use RMSE to assess accuracy and ME to determine bias. This not only informed us about the performance of our forecasts, but also guided us in fine-tuning them for better reliability.
Ultimately, our main motive goes back to being prepared for what's to come. When weather is predicted to rain, we prepare with umbrellas and raincoats. Similarly, when demand is expected to be high, having a demand forecasting process can help John Deere anticipate the peaks and valleys present in the demand cycle.